Welcome to Lesson 5 entitled Solubility Properties, and in class we did an activity where we mixed hexane, water, and a copper sulfate solute, and what we saw is the hexane layer formed right here, that's C6H14, and down here we got the water layer, H2O, and it actually mixed with the ionic copper sulfate crystals. It dissolved. So I asked you to explain why, and most groups looked at this, which is really nice, the headbutting and slapping idea, whereas the partially negative portion of the water molecule actually dissolved that full positive copper ion, it's actually copper plus 2, but that's okay, on the positive end of that ionic crystal, and the partially positive ends or terminals of the water molecule dissolved the full negative 2 portion of the sulfate ion. And the hexanes were kind of kicked aside. It's not that they were attracted to one another, but they were actually just pushed aside because they didn't have the same kind of intermolecular attraction. Now, whenever I ask you why something dissolved in something else, it's always about positive and negative attracting. It's either partially positive attracting to partially negative if we mixed two polar covalent compounds together that were different, or it's partially negative attracting the full positive on the ionic compound and the partially positive attracting the full negative. It's really just positive and negative attracting. So this is why nonpolar solvents are not soluble in polar solvents, because those nonpolar solvents do not have any net charge to be drawn towards them in solution. So let's go ahead and take some notes here. And the first thing we really have to investigate are intermolecular forces. So we called them IMFs before, and we're going to call them officially intermolecular forces. We can still think of them as IMF forces. And pay really close attention to this word inter, which means between. So these are forces not within the molecule, but actually between the molecules. Okay. And let's look at two distinct situations. So let's look at nonpolar covalent on one side, and let's look at polar covalent on the other. So a typical nonpolar covalent molecule we're going to look at here is carbon dioxide. So I'm going to draw two carbon dioxide molecules, okay, and they line up kind of like this. So, although the carbon here is partially positive and the oxygen is partially negative, there's no net dipole. But we do get a slight attraction between them, okay? So all nonpolar molecules do have a very small IMF. And this IMF is called a van der Waals attraction, but we're going to call it a London dispersion. It's the weakest of the intermolecular forces. All particles have them. And the London dispersion is not a real dipole, it's a temporary dipole. And it's kind of complicated, but for split seconds here and there, you do get an attraction. So even though this is partially positive and this is partially negative, okay, the shape of them force those dipoles to cancel out, but they do still exist. So depending on the rotation of those atoms, some dipoles can exist for a period of time, causing those attractions to happen. But it's important to remember that these really don't have an effect on the overall charge of the particle. So nonpolar particles do have a weak IMF attracting them. It's this temporary dipole that we're going to call a London dispersion force. The reason we did the bubble activity is because we're going to investigate in Cycle B what I really mean by this temporary dipole. So now let's look at a typical polar covalent compound. Now let's just go ahead and look at water, since we're so used to looking at water, and I lost my pen here for a second. There it is. So I'm going to draw one water molecule, and because of its bent shape, these dipoles on water do not cancel. Okay, so if I get another water molecule, It's going to line up like this. Okay. Those of you in biology know it's going to line up into kind of a hexagonal type shape. And here, we are going to get a stronger dipole. Okay. And this strong dipole here is called and it's really simple here, a dipole to dipole interaction. Really simple, just dipole to dipole. Now, notice this partially positive and this partially negative charge are not going anywhere. They are stuck. Okay? So instead of a temporary dipole, this is actually a permanent dipole. So it's important that you write this. It's a permanent dipole. It's what causes polar molecules to be stickier, if you will, than nonpolar molecules. So in summary, we have two types of intermolecular forces. We have London dispersion forces, which are weaker, caused by this temporary dipole that exists once in a while between the partially positive and partially negatives within the nonpolar molecule. And we have a permanent dipole, which creates this dipole-to-dipole intermolecular force. Now, all particles really can be said to contain London dispersion temporary dipoles. So even though this water molecule has definite permanent dipole-dipole because of the polarity of it, there actually is technically a London dispersion force happening as well. Okay, so there is a London dispersion intermolecular force. So you can think of it as this way. All particles have London dispersion intermolecular forces. In addition to them, polar molecules also have dipole-dipole forces. So you can even think about polar molecules as just having more intermolecular forces. Okay. So now let's look at how the intermolecular force actually affects the solubility. Okay. And in solubility, we often use the term like dissolves like. Now, a misconception, a lot of times people will say like dissolves like means polar dissolves polar and nonpolar dissolves nonpolar. Now, that's actually true, but it's better to think about it this way. Substances with similar intermolecular forces dissolve other substances with similar intermolecular forces. Like IMFs dissolve like IMFs. You can even squeeze in here IMFs, because it's those IMFs that are causing them to dissolve one another, like we saw in the lab. So let's look at a situation where this would perhaps be true. We could look at a nonpolar substance here. So if we had, let's say, some methane. So I'm going to draw one methane molecule. And we mix that molecule with some iodine. Now, this methane molecule is nonpolar. Okay? And the iodine molecule is also nonpolar. I'm just going to put them around it. Now, there isn't necessarily a strong attraction. I mean, we're going to get these London dispersion, really weak partial dipoles kind of connecting these guys, really weak London dispersion forces. But they're not repelling each other either, okay? So because they're nonpolar, they're going to exist with one another. It's kind of like all these lonely people that just are hanging out with each other and enjoying each other's misery, okay? But there is this temporary London dispersion dipole that does exist between them. So since both of these have London dispersion, the like IMFs dissolve the like IMFs, and they will dissolve in one another. But, when push comes to shove, nonpolar substances dissolve in other nonpolar substances. Well, let's look at a polar situation. Okay. So now let's take water. Let's say we had water, which has these permanent dipoles here. And let's say we dissolve something like ammonia in water. Okay? And ammonia is a trigonal pyramidal molecule that also is polar. And that's partially positive and partially negative. And we're going to get it lining up over here like this as well, where this is partially negative and these are partially positive. You guys should be able to draw those. And now what you see, since both of these molecules are polar, they both are going to have this dipole-dipole interaction here that's happening between them, where the partially positives on one and the partially negatives on the other are attracting one another. So they both have similar IMFs. Now, again, there are these London dispersion forces that are acting as well. They're always there, but it's really that dipole-dipole force that's causing them to attract. And it makes sense. In the lab today, we did something a little bit different, but it's the same effect. So in the lab, we put in some copper that was actually 2+, and the copper 2+, if we put it in here right now, we could even draw one in right now, would be attracted to that negative, partially negative on the oxygen, and the sulfate 2- will be attracted to all of these partially positive hydrogens. But again, polar or ionic, it's the positive attracting the negative. So let's do a little summary here of these notes. So the first thing for you to remember is polar substances dissolve other polar substances. So polar dissolves polar. Meaning the substances that have dipole-dipole intermolecular forces will dissolve substances that have dipole-dipole intermolecular forces. And when I say dissolve, what I mean is it's really soluble in it. Okay. Conversely, nonpolar substances dissolves nonpolar substances. Okay. What that means is substances that only have London dispersion intermolecular forces will dissolve substances that only have London dispersion intermolecular forces. Again, soluble is a word for dissolves. And in terms of the intermolecular forces, if we take nonpolar substances, NP, the intermolecular force that they all have is the London dispersion force, and that's a temporary dipole. It's a really weak attraction. For a split second in time, a dipole does exist. We will explore that some more. Now, if you take two polar substances, the reason they are soluble in one another is, yes, they do have that temporary dipole that we talked about earlier, but they also have, we'll draw that in here, they have that London dispersion force, and let's just draw that there so you can see visually that they have both. But they also have this dipole-dipole force. So we'll be talking about in cycle C why these polar substances are going to have higher melting and higher boiling points. And the fourth point I really want to make, and we'll do that right here, is that in terms of the strength of the intermolecular forces, the dipole-dipole is stronger than the London dispersion. So substances that are polar dissolve substances that are polar, and substances that are polar dissolve substances that are ionic, because you have these permanent charges or permanent dipoles that exist. Substances that are nonpolar aren't really attracted to one another, but they're not repelled either, and we get these temporary London dispersion forces that sort of allow them to be comfortable with one another. Those dipole-dipole forces are stronger than those London dispersion forces. Everybody has London dispersion, okay? But when you get to the polar situation, you also have that dipole to dipole, that partial positive dipole attracting that partial negative dipole. So let's look at a multiple choice question. This one I'm going to speak out, okay? I want to know which of the following which of the substances below are soluble in methane, CH4. So which ones are soluble in methane? CH4. Okay, the first one I'm going to draw up here is going to be PH3. The second one I'm going to draw up here is going to be XeH4. The third one I'm going to draw up here is going to be HBr. And the fourth one that I'm going to draw up here is going to be H2O. Press pause and solve that problem. Thanks a lot.